Can we can agree that gravitational pull has some degree of like difference as you get farther away from an object. An object 500 light years into space is not going to have gravitational pull from Earth.
Not much.
So, wouldn't that mean that if it were to orbit Earth at 500 light years away, there would be a specific amount of gravitational pull that it would have, rather than 1 light year away?
Right, the gravitational pull would be different.
Right. So where does that come into play with our equation, where it's gravity is a
The
constant?
total acceleration here is greater than the total acceleration here. The farther you are away, the lower the smaller the acceleration.
It's our R squared, or the R cubed.
Okay.
So whatever the radius is at whatever point in the orbit.
Are you talking, let's be careful about that. Are you talking about comparing planet to planet, or are you talking about one planet comparing different points within the orbit?
One planet at different points.
So the acceleration, the gravitational pull is stronger here than it is here.
Right.
And so there's a larger acceleration here.
Right.
And sorry, let's try this one more time. So your issue is
Big G is a constant.
correct.
Okay. If we write out the equation, big G is equal to mass of the center of the object divided by 4 pi squared, which is also the period, right?
So we have big G, mass of central object over 4 pi squared is equal to
R cubed over T squared. R big G is a constant. It doesn't change.
right,
Gravitational pull changes as we get farther away and closer.
right.
What happens between those two, what happens between the gravitational constant that keeps it constant rather than the gravitational pull that changes?
All right. This equation right here. This equation right here, I just used R because I assumed a circular orbit.
Right.
This R right here, this formula does not apply to what's going on here versus what's going on here.
Okay.
This is actually average orbital radius,
Okay.
if you want to get down to the dirty details.
So then G would be gravitational pull average?
This big G, that's still a constant.
Yeah.
Your total value.
But this ratio here for, if you actually, so I solved it for a circular orbit, but if you go into the calculus of it and assume elliptical orbit, then, and you can actually show it's gonna be an elliptical orbit, that this R right here is average radius of the elliptical orbit.
Okay.
So this applies to the entire cycle comparing one planet to another planet.
Okay.
It's not really appropriate to use this formula when you're comparing one planet at 2 different points in the orbit.
Okay. That's where I was confused.
Okay. Dan?
Is tangential acceleration going this way or this way?
Tangential acceleration is in the direction, it's either parallel or anti-parallel to the velocity. At this point, it's going that way. When it gets on this side over here, it's going opposite the velocity.
And which one is the velocity?
Velocity, there's a green arrow that's been sort of covered up. Velocity is in the direction of movement. If the sun suddenly disappeared, it's the direction that the planet would go in.
And what's that purple sign?
That circle right there?
The other one? The one on the left? The up?
What is that?
Uh-huh.
That was just showing at another point in the orbit, we still have centripetal and tangential accelerations. Now, Kepler did not have a clue why any of this worked. He saw that it worked, published it, shows up in textbooks. Newton starts with one premise-ish, I guess 2 at this point mathematically. The formula for gravitation, the fact that it's inversely proportional to the distance squared and directly proportional to the product of the masses. And that F equals ma. Starting with those two premises, you can derive all of Kepler's laws. He also invented calculus along the way. You Leibniz fans, yes, I'm sticking by that Newton comment. So imagine you spent 40 years of your life, Kepler, working on this, and you're in a bar, you felt a good day, you're almost done, and you're sitting down, and Newton comes along, and they start chatting about what they're doing. And Kepler talks about, yeah, I spent the last 40 years trying to figure out how the planets move around the sun and coming up with 3 rules that sort of describe it. I'm almost verified it, feeling really good. Newton said, oh, that's what you're working on? You got an afternoon, I can show you how to do it. I say, fortunately, Kepler was dead by the time Newton was alive, or was doing his work at least. Because just imagine you spent 40 years of your life working on this one problem here, and someone else can do it in an afternoon now.
You said 40?
40.
Okay. At first I thought you said 4 and I was confused.
I think there's a cruelty joke skit in there somewhere. So one of the reasons, though, that Newton's laws were accepted so quickly, though, is the fact that he could derive Kepler's laws. The fact that we already had empirical data showing behavior of planetary motion, and Newton could derive it. Newton did come up with one other twist to it, the fact that the sun's being pulled by the Earth, so the sun does wobble a little bit as the Earth goes around it. Actually, it's getting wobbled in however many things going around the sun that we're pulling it. However, on that note, I think we are done with 6,
That's 6?
chapter 6. Which means assignments, dates, deadlines.
Every day.
So, what's the set? This is in November. So, November 1, 3, 4, 5. The element is Veterans Day, but that doesn't affect us directly, at least. What I'm inclined to do, we could have the test on the 5th. I'm just sort of toss out a trial balloon here. We have the test on 4, 5, and 6 on the 5th. That's a week from this Friday. I don't officially assign master set 6, I'll just post solutions for it. So that's where my thinking is right now. But since we're done with 6, the only thing that I'll be doing for 4 through 6 at this point is, well, there's the test. There's the quiz on Friday for chapter 5, and the master set for 4 and 5 applications on Friday. But I would start new material next time we have class, so I don't know what to talk about Wednesday also. Anyone with a counter proposal to my proposal of the test on 4 through 6 on Friday the 5th?
You said 4 through 6?
Yes.
Okay.
Is that your like second half of it? Because remember you were talking about how you have like, yeah, test one.
Test 1B.
Okay.
It is officially a second test. It's 1B for historical reasons. So chapters
4 through 6.
All right, so let's talk about Wednesday. The lab, the other force lab that I have just is horrible. And I don't want to do it. So therefore, what do? Do we start doing a lab on the material that we haven't covered yet? I'm actually not inclined for that. What I propose is that this Wednesday, as in 2 days, we actually just have a long class. Instead of subjecting you to a horrible lab. And since it's an extended period, also, I will try to drone and be as monotone as possible.
You're gonna have to try harder than that to make me fall asleep.
Oh, challenge accepted. So, nothing to print out. And I think on that note, have a safe afternoon. And what the heck, have a safe tomorrow also. Just be safe in general.
So I was thinking about this. It seems like how velocity and acceleration in a two-dimensional problem. If they're in the same direction, object is speeding up. If they're in opposite directions, the object is slowing down.
Yes.
But with this, it seems like it's the tangential acceleration, the direction of tangential acceleration. If there's like an acute angle between the tangential acceleration and the
acceleration equals
acceleration, the total acceleration.
If there's an acute angle between
Tangential
the
and.
velocity and the full acceleration,
Right,
it'll speed up.
it'll speed up, if it's like an obtuse angle, you said an opposite direction, so you just meant like pointing in away from.
If there's part of that acceleration that's directly opposite the velocity, it'll slow down.
that's, so you gotta divide divide time.
It seemed like
Oh,
in
yeah.
Kepler's law example, we were running through, it brought memories of, fourth grade or something, when we had the old school projectors. And my teacher was trying to help us understand why all of the angles in a triangle equal 180. And I was like, no, it can't be, it can't, I was so upset, so I came up, she had me come up there and draw the most absurd triangle I could think of, like some really extended triangle and like measure it and everything, proving that all of the, they all add to 180.
What grade was that?
I was in fourth grade, but I don't remember, something in later elementary school.
There, have you read Flatland or Sphereland?
No?
Flatland, or Romance, a romance in many dimensions, I think it's the subtitle.
Okay.
I just did like
It
I just did 2
deals with a two-dimensional world. There's a square in a two-dimensional world trying to figure things out, and interacts with one-dimensional and zero-dimensional, and like three-dimensional creatures.
Yeah, but I'm pretty sure
And-
you factor in the
In Sphereland, basically it was an update to it. Flatland was written in the 1890s, I believe it was. And so there was something written in the 60s or 1960s or 70s called Sphereland, which actually looked at that, and there was one of the beings in this two-dimensional world who kept looking at the angles of a triangle and said, they're not adding up to 180. And that's because once you start getting into curved space, they don't add up to 180
Right.
or necessarily. So you potentially were just ahead of your time.
Maybe I was. Maybe I was.
I can't believe your fourth grade teacher didn't bring that up. Well, Euclidean geometry,
Oh, no. It was a very, very hard day. Well, thank you.
yep. Kill the recording.
I just wanted to say,